Hello all, welcome to online lecture series on Laplace transforms. This is lecture number 14. In this lecture also we'll continue to learn about the properties of Laplace transform. Here is one another interesting property of Laplace transform of integrals. In the last lecture we derived the property of in Laplace transform of derivatives. This is Laplace transform of integrals, which states that if Laplace transform of f of t is known to us, then we can find Laplace transform of integral of f of u du within the limit 0 to t. It is given by f bar of s by s, where f bar of s is L of f of t. So Laplace transform of integral 0 to t f of u du is equals to L of f of t by s. So first we'll prove this. So for that we take integral f of 0 to t f of u du, this integral for which we are supposed to find a Laplace transform. We take this function as g of t. G of t is equals to integral 0 to t f of u du. Then g dash of t, that is derivative of g with respect to t, is equal to d by dt of integral 0 to t f of u du. Now to derive this integral, we use Labanate's rule or derivative under integral sign. What does it state? Let us look into the Labanate's rule or derivative under integral sign. Before that, what is g of 0? Let us check what is g of 0. What is g of 0 here? If we take t is equals to 0 in this, we get integral 0 to 0 f of u du. Integral 0 to 0 f of u du is equals to 0. Therefore, g of 0 is 0. So, we'll use this value of g of 0 to prove this property in the coming steps. So, before applying this, we'll find this derivative of d by dt of integral 0 to t f of u du. Let us derive this. Labanate's rule of integration or differentiation under the integral sign states this: d by dx of integral f of x comma t dt within the limits a of x to b of x. The limits are functions of x, a of x, b of x, and the function is f of x comma t dt. This is equals to f of x comma bx into derivative of bx minus f of x comma ax into derivative of ax plus integral a of x to b of x dou by dou x of f of x comma t dt. Previously also we used Labanate's rule, but there the limits are constant. Because the limits are constant, the first two terms became 0 and we have taken the derivative inside the integral as a partial derivative. So only this term remained, because in that case the limits a of x and b of x are constant. So the derivative of a of x and derivative of b of x became 0. So these two terms became 0 and we have only this term. But in this case the limits are not constant because the limits are 0 to t. So if you observe here, what happens in this Labanate's rule of integration is we replace this t with b of x, the upper limit first, into derivative of the upper limit minus f of x comma, the t is replaced with lower limit a of x into derivative of that lower limit a of x plus integral dou by dou x of f of x comma t dt. Now let us apply this Labanate's rule of integration to g dash of t. So now to find g dash of t, by applying this rule, g dash of t is given by d by dt of integral 0 to t f of u du. Now compare this derivative here in the Labanate's rule and the derivative d by dt of integral 0 to t f of u du. So this is equals to f of t d by dt of upper limit. What is upper limit here? Upper limit is t. So dt by dt minus f of t is replaced with lower limit a of x here. So here lower limit is 0. So this is f of 0 into d by dt of lower limit, that is 0, plus integral 0 to t dou by dou t of f of u du. Okay. Now this dt by dt is 1 and derivative of 0 is 0. And look at the third term here. Partial derivative of f of u with respect to t becomes 0 because there are no t terms here. So this goes to 0. So therefore this is equals to f of t. This is 0 and this is also 0. So it is f of t. Therefore, g dash of t is equals to f of t. Okay. Now let us go back to the property again. So consider Laplace transform of g dash of t. What is Laplace transform of g dash of t? Laplace transform of derivative of g of t, which we have already derived this property. It is s times L of g of t minus g of 0. So let us substitute all the values here. G dash of t, L of g of t and g of 0. So if we substitute all the values, we get L of g dash of t is f of t, which we have already derived in the previous slide. G dash of t is equals to f of t here is equal to s into L of g of t. We assume g of t as integral 0 to t f of u du. So we substituted in place of g of t, and g of 0 we proved it as 0. Therefore, g of 0 is equals to 0. Hence, this is equal to s times Laplace transform of integral 0 to t f of u du. Therefore, Laplace transform of integral 0 to t f of u du is equal to L of f of t by s. So, this is how we derive this formula. So, if you have any doubts, you can go back and again go through the proof. So finally the statement is Laplace transform of integral 0 to t f of u du is equal to L of f of t by s. Laplace transform of f of t by s. Now let us apply this property to derive Laplace transform. Let us see where this property can be applied in examples. Evaluate integral Laplace transform of integral 0 to t e power minus t cos t dt. So we are asked to evaluate the Laplace transform of this integral function. So let us apply this property which we have proved now. Laplace transform of integral 0 to t f of u du is Laplace transform of f of t by s. So here Laplace transform of integral 0 to t e power minus t cos t dt is equal to 1 by s times Laplace transform of f of t. What is f of t here? E power minus t cos t. So now we have to derive this Laplace transform of e power minus t cos t. So what property shall we apply here? The first shift property, because it is of the form L of e power at into f of t. What does first shift property says? This is equals to L of f of t, that is L of cos t, with s replaced with s plus 1, because L of e power at into f of t is equal to L of f of t, where s is replaced with s minus a. This is using first shift property. Now what is L of cos t? L of cos t is s by s square plus 1, because L of cos at is s by s square plus a square, and a is 1 here. Therefore this is 1 by s times s by s square plus 1, where s should be replaced with s plus 1. Now we simply replace s with s plus 1 in this term. Then we get 1 by s times s plus 1 by s plus 1 whole square plus 1, that is 1 by s times s plus 1 by s square plus 2s plus 2. Therefore Laplace transform of integral e power minus t cos t dt is equal to s plus 1 by s into s square plus 2s plus 2. Now let us see another function where the property of Laplace transform of integral can be applied. Evaluate Laplace transform of integral 0 to t 1 minus e power t by t. Again using the same property, L of integral 0 to t f of u du is L of f of t by s Here f of t is 1 minus e power t. Therefore, Laplace transform of integral 1 minus e power t by t is 1 by s times L of 1 minus e power t by t. So, now to evaluate Laplace transform of 1 minus e power t by t, we use L of f of t by t formula. What is L of f of t by t? It is integral s to infinity L of f of t ds. L of f of t by t is integral s to infinity L of f of t ds. So, we apply this formula here. F of t is 1 minus e power t. So, this is 1 by s times integral s to infinity L of 1 minus e power t ds. L of 1 minus e power t is L of 1 minus L of e power t. L of 1 is 1 by s. L of e power t is 1 by s minus 1. Now, integral of 1 by s is log s minus integral of 1 by s minus 1 is log s minus 1 within the limits s to infinity. So, this is 1 by s times log s minus 1, and log a minus log b can be written as log a by b. But if we directly substitute the upper limit infinity here, we get undefined form. So, we divide s by s minus 1 with the highest power of s. The highest power of s is here s. Therefore, if we divide numerator and denominator with s, we get 1 by s times log of s by s is 1 in the numerator, and in the denominator s minus 1 by s is 1 minus 1 by s. Now, if we substitute the limit, upper limit infinity, 1 by infinity becomes 0 here. So, log 1 minus lower limit is anyhow s. So, that is 1 by s times log 1 is 0 minus log of 1 by 1 minus 1 by s. Simplifying back, we get 1 by s times log of s minus 1 by s. Taking a LCM here, and minus is this minus is taken to the power, and that becomes reciprocal. So, this is 1 by s times log of s minus 1 by s. So, if you observe here, we are applying different properties of Laplace transform. The first shift property, Laplace transform of f of t by t, Laplace transform of t into f of t. So, we apply these properties to derive Laplace transform of different complex functions also. So, here is one such another function here. Evaluate Laplace transform of e power minus t integral 0 to t sin t dt. So, looking at this function, can you identify the properties which we are supposed to apply here? Because we have e power at into f of t, we should apply first shift property. And we have Laplace transform of integral. So, we have to apply the Laplace transform of integral formula. And inside the integral, we have L of sin t by t. That is, we need to apply L of f of t by t. So, totally here we apply 3 properties of Laplace transform. So, first, because we have e power minus t term here, we use first shift property. This is of the form L of e power at into f of t. F of t is here integral 0 to t sin t by t dt. So, L of e power at into f of t is L of f of t with s replaced with s minus a. Therefore, this is L of integral sin t by t with s replaced with s plus 1. Now, so first let us completely evaluate this Laplace transform, and at the end we replace s with s plus 1. Now, look here. We need Laplace transform of integral. What is Laplace transform of integral? We just derived the property, isn't it? Laplace transform of integral of f of u du is L of f of t by s. Therefore, this is 1 by s times L of sin t by t. We use this property here. Laplace transform of integral. Now, to evaluate L of sin t by t, we use the property L of f of t by t. What is L of f of t by t? It is integral s to infinity L of f of t ds. Therefore, L of sin t by t is equal to integral s to infinity L of sin t ds. What is L of sin t? L of sin t is 1 by s square plus 1, because L of sin a t is a by s square plus a square. So, hence we get 1 by s times integral s to infinity 1 by s square plus 1 ds. Integral of 1 by s square plus a square is 1 by a tan inverse of x by a. A is 1 here. Therefore, this integral is tan inverse of s. So, 1 by s times tan inverse s within the limits s to infinity, and after substituting the limits and simplifying, then we replace s with s plus 1. So now let us substitute the limits here. Upper limit is infinity and lower limit is s. Therefore we get 1 by s times tan inverse infinity minus tan inverse s. What is tan inverse infinity? When the tan value becomes infinity, goes to infinity at pi by 2. So tan inverse infinity is pi by 2. And hence this is 1 by s times pi by 2 minus tan inverse s, and we all well know that pi by 2 minus tan inverse s is cot inverse of s, because tan inverse s plus cot inverse s is always equals to pi by 2. So pi by 2 minus tan inverse s is cot inverse s, and hence this is 1 by s times cot inverse s, where s must be replaced with s plus 1. Now because this entirely the inner term is simplified completely, no other Laplace transforms or integrals to be simplified here. So now we can replace s with s plus 1. So this gives cot inverse of s plus 1 by s plus 1. Therefore Laplace transform of the function e power minus t into integral 0 to t sin t by t dt is equals to cot inverse of s plus 1 by s plus 1. So in this way we can apply the properties of Laplace transform to evaluate Laplace transform of functions. So you practice these questions. Evaluate Laplace transform of integral 0 to t e power t sin t by t. So first you have to apply the property Laplace transform of integral, then first shift property because you have e power t here, then f of t by t. So totally you need to apply 3 properties here. Similarly, the second one is evaluate L of e power minus 3t into integral 0 to t 1 minus cos t by t. First apply first shift property because you have L of e power at into some function. Then Laplace transform of integral, and then L of f of t by t. Again 3 properties. Next one is evaluate L of t into integral 0 to t e power minus t sin t by t dt. Here also you need to apply 3 properties, 4 properties in fact. First one is L of t into f of t. What is L of t into f of t? Laplace transform of t into f of t is minus d by ds of L of f of t. Then use Laplace transform of integral and then apply first shift property. Then apply L of f of t by t. So totally in this problem you need to apply 4 properties of Laplace function. So try these problems. In case of any difficulty in solving or in case of any doubts, please contact me. Thank you for watching the video. Keep learning. Bye.